Hello Year 11. Following on from what we talked about in class, in this video I'm going to work through an example that demonstrates how the ambiguous case of the sine rule works. And to begin, I will draw up the triangle that I showed in class, although what I'll do is I might draw it just slightly differently so that it's a bit easier to follow. Firstly, I'm going to not draw it upside down the way it was shown in class. I think that will help, and I'm also going to try and draw this as accurately as possible. So one of the sides was noted as having a length 10, so I'm going to actually draw this to have a length of 10 centimeters. The other side had a length of 6, so I'll draw this side to have a length of 6 centimeters. I'll then connect those two lines so that we have our first triangle, and I will we'll call this triangle A, B, C, and as I've shown, the length of AC had a length of 10. Oh no, what's going on with my pen? So 10 centimeters, great, and then the length of AB was 6 centimeters. Now I also want to add another side, also of length 6, that comes from point A and connects to the line BC, but with a length of 6. And so if I just rotate the rectangle until we get those two connecting, that looks pretty good. Okay, so this is not perfect, but at least somewhat accurate. So I'll add this new point, I'll call it D, and that also, the line AD also has a length of 6 centimeters, making ABD an isosceles triangle, and that will be useful to keep in mind for later. Now, in the triangle I showed in class, which I don't think was really drawn very accurately, the angle ACB was noted as being 30 degrees. But if I just put a protractor here, and I can't show the protractor on screen, I don't think this program has a digital protractor, but just using a physical one, that angle ACB is closer to 35 degrees. So I might just note that as being 35 degrees rather than 30, just so that again we're dealing with a somewhat accurately drawn triangle. And the two angles that we're really interested in are angle ABC and angle ADC. They're the two that we can use the sine rule to find, and I might note them as alpha and beta. So we'll say angle ABC we'll call alpha, and angle ADC we'll call beta. And what I'd like to do is demonstrate how the sine rule plays out in terms of finding each of those angles. But before I do those calculations, there are a few things we can notice about alpha and beta. And I think the first thing worth noting is that alpha is not equal to beta. Those two angles are clearly not equal, we can just see, and that's partly why I wanted to draw this triangle accurately, so that we can clearly see that those two angles aren't equal. And part of what's different about them is clearly angle alpha is acute, and angle beta is obtuse. And just in case those definitions are a bit rusty for you, acute angles are less than 90 degrees, so angle alpha is clearly less than 90 degrees, and obtuse angles are greater than 90 but less than 180, and clearly angle beta is greater than 90 but less than 180. So, okay, that's probably all we need to consider before we start doing the mechanics of the calculations. So let's begin by finding alpha. And to find alpha, we can use triangle ABC. So I'll note over here, in triangle ABC, we can say that the sine of alpha over the length of the side opposite alpha, being 10, is equal to the sine of 35 divided by the length of the side opposite 35, which in triangle ABC is 6. And that means I can say that sine of alpha is equal to 10 times sine of 35 over 6. And that means alpha will be equal to the inverse sine of 10 times sine 35 all divided by 6. And at this point we can go to our calculator and enter that. So we want to calculate the inverse sine of the fraction 10 times sine of 35 all divided by 6. And when I press equals, we get 72.9 or 72 degrees, 55 minutes, 57.76 seconds. So let's just call that 73 degrees to the nearest degree. So we'll say 73 degrees to the nearest degree. And I think hopefully that makes sense in terms of we noticed that alpha is acute. When we calculated alpha, we got 73 degrees, and that is less than 90. So that all seems to have worked fine. Now, let's think about beta using the sine rule. So for beta, we can use triangle ADC. So I'll write in triangle ADC, the sine of beta divided by the side opposite beta, which is 10, is equal to the sine of 35 divided by the length of the side opposite 35, which in triangle ADC is also 6. And at this point, without even doing any rearranging, clearly the starting point here is the same as the starting point we had when we were finding alpha, albeit instead of alpha the angle is beta. But if we were to follow the same mechanics, and I'll just do that I guess for completeness, we would end up with sine beta equals 10 sine 35 over 6. So beta would be the inverse sine of 10 sine 35 over 6. And again, I don't need to go to the calculator. We already typed that in earlier, and so we got beta being 73 degrees to the nearest degree. And clearly here is where the ambiguity arises, because we already noticed alpha is not equal to beta. Alpha is acute, so alpha being 73 makes sense, but beta being 73 degrees does not make sense. Beta should be obtuse, but here the application of the sine rule is spitting out an answer that doesn't make sense. It's ambiguous because we've got two clearly different angles, yet a formula that's giving us the same value. And what we can do at this point is come back to triangle ABD, maybe I'll highlight that. Triangle highlighter. Yeah, triangle ABD, I noted earlier, was isosceles, because both the two of the sides are equal, being a length of 6. So what that means is angle ADB must also be equal to alpha, because the base angles of an isosceles triangle are equal. So ADB is alpha, and that means we can now observe that alpha plus beta, this entire angle here, must be equal to 180 degrees because angles on the straight line add up to 180. And so over here where I noted everything we know, we can also note that where's my pen gone? Alpha plus beta is equal to 180 degrees. So actually, if I want to find beta, I can simply take 180 degrees and subtract alpha. And so let's do that. So if you were, say, trying to do a question like this on an exam, you could, at the point where you get beta equals 73 degrees, you could say, but beta is obtuse, therefore beta must actually be 180 degrees minus the answer that we got. And so here we can say, if we need to go to our calculator, we can say 180 minus 73, and we see that beta must be 107 degrees. And again, that's to the nearest degree because alpha was to the nearest degree. But that makes more sense because we noticed beta was obtuse, 107 is greater than 90 but less than 180. And so that is the result that is not ambiguous. That makes sense in the context of this triangle. And that is how the ambiguous case of the sine rule plays out. It is possible to draw up two different triangles with the similar dimensions but very different unknown angles. And so whenever you're dealing with the sine rule, you need to be conscious of whether the unknown angle you're finding is acute or obtuse. And if the triangles that you're dealing with are drawn to scale, then you should be able to, just by observing, notice whether what you're finding should be acute or obtuse. But often in exams you'll notice that diagrams have an indication that they are not to scale. And when that's the case, you should expect that if you're given a diagram and you're being asked to find an unknown with the sine rule, you should be told, ideally in the question, whether the angle you're trying to find is acute or obtuse. That would be a good practice from a question writing perspective. But if you happen to come across a question where it's not explicitly told to you whether the angle is acute or obtuse, you probably then simply need to either observe it, or maybe there's some other information in the question that makes it clear which case you must take. So the way you can work through it is you apply the sine rule as you normally would, see whether you get an acute or obtuse angle, and then think about whether that is what you should be getting. And if it's not, you take 180 degrees minus whatever initial answer you got. So hopefully that example has kind of helped you understand how the ambiguous case of the sine rule arises, and hopefully now if you do come across it, you'll know what to do. All right, tick boom. We bring the